actually train policies in simulation such that they can generalize to the real world. And as I said, learning in simulation has opened up promising avenues for robot learning, because we can get lots of free data, lots of cheap data in simulation, and we have high speed of training. We can do lots of trial and errors without any danger, and we would have much more time to devise better algorithms. And there are many simulation environments that are developed by different groups, such as Mujuko, Gazebo, Define Lab, and Vizdoom, and Atari. However, the darker side to this story is the reality gap. And by learning policies in these simulated environments and worlds, it is hard to understand how to generalize to the real world. And transfer learning approaches, which are pretty well known in computer vision, actually need to have some amount of the target domain to use for fine-tuning their models, or use during a joint training kind of procedure. And there are some approaches in that regard from different groups. However, what we want to look at here is actually how can we train policies, and how can we learn these policies in simulations such that they can directly generalize to the real world. And our solution for this problem is through simulation, or also known as domain randomization. And this approach is orthogonal to the conventional transfer learning approaches, so that we can learn in simulation. We can also add some transfer learning at the end, but our goal here is to show how can we actually learn policies that can generalize to real world directly through domain randomization. And we showed that by highly randomizing the rendering setup at the training time, such as textures, lighting, camera orientation, having different floor plans and different textures, we can train policies that can generalize to the real world and also unseen environments with substantially different appearance models than the ones seen at the training time. And in this case, we could address the limitations of reinforcement learning for trial and error in the real world, and address the need for a huge amount of data for training the policies. And given the effectiveness and efficiency of CAD2RL and our proposed domain randomization approach, there have been several follow-up works to CAD2RL from different groups, such as OpenAI, Google Brain, Imperial College London, and Australian Centre for Robotics Vision, where they showed that they actually could use the same domain randomization approach and deployed on other robotics problems, such as manipulation. In this case, they tried it for grasping and reaching and picking and placing, and they showed that this idea is effective, and it can generalize to other robotics problems as well. And this is pretty important because learning in simulation can open up lots of opportunities for robot learning. And this has been pretty exciting for us. But before moving to our next research questions, I found it pretty worthwhile to mention that simulated data augmentation had been used pretty much a long time ago in computer vision. So image level photometric distortions, such as color manipulation and adding jittering noise or random crops, had been used in computer vision to augment the data. Perhaps one of the earliest versions of using this idea had been in the seminal work of Pomerleau in 1989 in the Alvin system, which is known to be one of the very earliest prototypes of self-driving cars, where they actually generated some simulated road data here. And later, for object detection and in deep learning, they added these photometric image distortions to improve the generalization of the deep models. So next, we want to see how we can learn stable policies via CAD2RL without needing to do bootstrapping, and we propose to use Monte Carlo policy evaluation for this. So to look at what our solution is, let's walk through the steps one by one. So as I mentioned earlier, the input to our system are single monocular cameras from the mounted camera on the drone without any depths, and these forms our observation. So we discretize the image space into a grid of bins where the choice of each bin could be the choice of the action. And we take multiple actions at each step and do multi-step rollouts, some of which will make the flying directions in the corridor. Some of these directions might lead into collisions and some not, which we will take it as the notion of success versus failure. And using this environment feedback, we make our reward function, which reflects the probability of colliding into an obstacle. Using this reward function, we compute Monte Carlo return estimates, which is the summation of the return and the decay return values. And by taking this approach, we will end up with a data set of observation, action, and returns, which we will use to update our policy. So basically, we try different actions given each observation, and we will end up with a dense map of success versus failure probabilities. And we use a deep fully convolutional neural network to learn to predict this probability map. And in practice, we use VGD16 architecture for this thing. Okay, next we want to see how these policies, which are totally trained in simulation, can be evaluated. One thing that I want to mention here is that despite the conventional method for evaluating reinforcement learning, which has emphasis and focus on mastery rather than generalization, here we want to evaluate the generalization of our method because we think this is important since in robotics we are having many situations where our robots will encounter a real world and they should be able to generalize to unknown environments and situations. So instead of like taking the practice of reinforcement learning where they train and test on the same game or in the same environment, we looked at evaluating on 3 different environments, none of which had been seen at the training time. So first, we evaluated on the real world. We evaluated the probability, the collision occurrence in 2 different hallways, and we found out that our RL-based policies can experience collisions almost 50% less than the supervised learning version where it didn't have the Monte Carlo rollouts. And we also tested on a realistic simulated environment, which is a close proxy to the real world. And the advantage of using this environment is that we can do rigorous evaluations by restarting the drone from different locations with different orientations. Like these red dots show the initialization of the flight at different locations of this building, and we could perform this multiple times to actually have a rigorous performance evaluation. And we saw that we could generalize to this unseen world. And as I said, this is a very close proxy to the real world because the geometry comes from a SLAM system which has captured the interior of Corey Hall in UC Berkeley. And the textures come from real images captured from the different viewpoints in the building and are stitched together. And we saw that, again, we had consistent performance of outperforming other supervised learning approaches and prior work in the baseline. And to see the behavior of the policy, we visualized the trajectories that are taken by the drone in this building and showed them with the color map which showed the direction of the flight. And we saw that once the drone had been flying with our proposed CAD2RL controller, it could actually have a very good coverage over the whole floor plan because it didn't experience the collisions and could just go forward and kind of cover the whole building. Whereas in the supervised version and a prior work, since the drone makes many collisions, then it cannot even make a good coverage for the whole building. So this was quite amazing. And finally, we also tested on a synthetic environment, which is similar to, but not exact to the environments that we use for training. Here, the floor plan is much more complicated than the ones we use at the training time, and the textures are not seen at the training time. And we evaluated our performance here, and again saw the boost. So the question that arises here is that from learning in these simulated environments, and acting in the real world, how much randomization do we need, and what is the importance of randomization? To answer this question, we opted for a proxy task of free space prediction on RGB images, and for doing this, we collected some RGBD data of several different hallways with various conditions of lighting and also moving the camera so that we have some motion blur and varied angles of viewpoint. And we just used this data for evaluation. We didn't use it for training. And the task, and we actually use the depth channel as a ground truth for where free spaces are and where not. So we trained different networks with different amount of randomization, and these networks are only trained in the simulated data, but the amount of randomization varies. And we saw that with a model that has a good amount of randomization, we can outperform other simulated environments and simulation setups where they see less randomization at the training time. So we concluded that more randomization results in higher precision, and the takeaway is that if we can devise very diverse environments and take more time to do more randomization in terms of varied conditions of textures, lighting, and all the setups of simulation, we can boost this performance in the real world. And again, I would like to emphasize that this would be free in terms of the dangers of trial and error in the real world, and the learning speed would be much higher, and this approach wouldn't need human in the loop for collecting the data, and also annotation. So to conclude, we see that deep reinforcement learning, CAD2RL robot learning is very data inefficient. And simulation can address this complexity by providing us this environment which are fully annotated in the simulation. We showed that Monte Carlo policy evaluation can be used as a stable method for learning policy via CAD2RL, and simulation randomization is a promising approach for direct sim-to-real transfer. The material in this talk had been coming from the real single image flight without a single real image paper that was presented in RSS conference. And I would be happy to take questions.